All right, so we're starting today with the definition of concave up and concave down because that's going to be kind of the theme of today's work, is we're going to be looking at how do we know when a graph is concave up or concave down, and then actually finding that for given equations. All right, so for these you can see some illustrations about them. The definition is very technical in terms of where the tangents are. So it's below its tangent lines or above its tangent lines. And that's a very good technical definition as a way to be able to test it. Practically speaking, though, you might prefer to also give yourself a quick little sketch about what concave up and concave down look like. So like this first one here is concave up. You notice that it's kind of like, well, kind of like our parabola that opens upward, like a smiley face. That's actually a way that you can remember what concave up looks like. Up, you're normally smiling. If you're down, you're frowning. A way to kind of envision it like if we're building little happy faces here or whatever along the way. Now, knowing what concave up and concave down actually mean allow us to now look at how can we know what they're actually going to look like. So here's a couple different graphs. For this first one here, is this graph, this f of x graph, is that concave up or is it concave down? That is concave down. So this is an illustration of a function that's concave down. And this one here, is this concave up or is it concave down? It's concave. You know, it's U. I mean, it really looks like a U even. It's concave up. And technically, if we wanted to, we could actually draw the tangent lines in and see that all the points on the graph are below the tangent line and all that kind of stuff. All right, so knowing that each of these on the top are related to this concave down function, notice what concave down means is happening. What's happening in our derivative? Notice our derivative is decreasing. In this particular case, it's going straight down. It doesn't have to be straight, but it's decreasing all the way along. That's what makes it concave down, is it's always being pulled downward. But notice then, if it's always decreasing, notice what that means for my second derivative. If it's always decreasing, how fast it's changing, that is a negative slope, that means that our second derivative is always negative as well. The same kind of thing we can see happen actually with this concave up over here. Because if it's concave up, it's always being pulled up. So we're always increasing the rate at which we're changing, which means that my second derivative is always positive. And so then we can then see that this will in fact play out across the board. This is actually a rule we can then define, where we can know that anytime it's concave down, your second derivative is going to be negative, and anytime it's concave up, your second derivative is going to be positive. And so with that in mind, we have the concavity test, how we can actually test using the second derivative to know if it's concave up or down. So you add this to your notes. All right, and then one more piece to add to this slide is we also have to deal with the point of inflection. A little bit of vocabulary here. A point of inflection basically is a point where we change from concave up to concave down, or concave down to concave up. So at a point of inflection then, what must be true about the second derivative? Well, that's got to be where it actually equals 0. We're going to start by practicing these ideas visually. So we're going to be taking a look at this graph and figuring out what are the intervals of concavity and where are the inflection points in this particular graph. Now, if it helps you, go ahead and start by making a sketch of the graph. All right, and so I'm going to start by thinking about that definition of concavity, where if something is concave up or concave down, then all the points on the graph around it are either above or below the tangent. So like if I sketch in the tangent at some point over here, notice the graph is below all the points on that tangent, which means that over here I'm concave down. The question then is, how far does the concave down section go? Well, continue to draw tangents there it's all below the tangent. Here, it's all below the tangent. If I go over here, all of a sudden the graph is above the tangent, so it's got to happen between those. And so really what you're doing is you're looking for basically where's the tangent going above and below it. It's where that change is happening for that tangent. And so at this particular graph, we can see it looks like it's happening right around that point. So it looks like it's happening right at 3 to divide between them. So that means we just found a point of inflection. So we know there's going to be a point of inflection at 3. All right, where does it look like the next point of inflection takes place? Well, envision those tangent lines, or the graph's above the tangent line there, graph's above the tangent line there. It's really following kind of that same pattern, because then the graph is below the tangent line. So it looks like this one's happening about the same type of place, just on the other side. So I'd say that one's happening at 5 for that point of inflection. Now between those 2 points, between 3 and 5, are we concave up or concave down? Up. Yep. And then after that, it actually does the same kind of thing that we saw before. Notice it's that downward motion, you know, the frowny face kind of an idea. So that is concave down in here. And so knowing that, then I can see that it's concave down on the interval from negative infinity up to 3. Sorry, yeah, positive 3. There it's concave down. From 3 up to 5, it is concave up. And from 5 up to a positive infinity, that's back to concave down. Now for the points of inflection, I need to go back to those a little bit. Because for points of inflection, in this particular graph, actually all we can say is that x equals 3 and 5. That's all we really can do based on what we can see here. But I do want you to be aware that if I can actually know what the y-coordinates are of that point, so let's actually give it a name. Let's call that a y-coordinate of 1. Then we would actually include that as a coordinate pair, and we'd say it happens at 3, 1, and 5, 1. In this case, they both happen to be at the same height. That certainly will not be the same on every single graph. But typically, if we can, we want to give both the x and the y coordinate. We're now going to practice this same idea of finding concavity and points of inflection with this equation. So write this problem down first, and then we'll work it through together. So whenever I see it's asking about the concavity or points of inflection, I know that what I need to do first is find the second derivative. Okay, and in order to find the second derivative, I need to first find the first derivative. So let's find f prime of x. Go ahead and find that derivative. And for that derivative, you should get 12x squared plus 6x minus 6. Now, the first derivative for our purposes here at the moment, all it's useful for this question is getting us to the second derivative. But remember the work that we've been doing the last few lessons where we've seen that we could use that to find the local max, local min, and some things like that as well. We just aren't doing it in this particular problem. All right, so I do want to use that now, find the second derivative. We should get 24x plus 6. Now, I find that because I now need to figure out where are those points of inflection. Because if I want to know where the intervals of concavity are, I need to know where those intervals change from one to the other. And they happen to change at the points of inflection. So, to find those, I plug 0 in for my second derivative. So we go 0 equals 24x plus 6. And then solve for x. So that means subtract 6 from both sides, divide both sides by 24, reduce, you should get negative 1/4. Now for both parts of this problem, to find the intervals of concavity and to find the inflection points, that is the main piece of information I need, because based just on that, I can now go ahead and find the intervals, because my intervals will go from negative infinity up to a negative 1/4. and then -1/4 up to a positive infinity. The only thing it hasn't told me yet is on which of those intervals is it concave up and when is it concave down, which we will need to find. The other thing I'll need is the inflection point. The inflection point, remember, is going to be a coordinate pair. It's going to be -1/4, comma, the y value. So we'll need to find that y value as well. All right, let's start by going up to our intervals. So within each of those intervals, I need to know, is it concave up or concave down? Remember how I know that? I know that by figuring out when is the second derivative positive or negative. So I'm going to take some point from that interval and plug it into the second derivative. So like for this first interval, I'm going to use -1. It seems like a nice, easy number. So if I plug -1 in for x, 24 times -1 is -24. -24 plus 6 is negative. So since that gave me a negative number there, that tells me that it is concave down. I repeat the same process with the second interval. Yes, we do need to check the intervals. We can't just assume that it's got to be up because it's next to it, because that won't always be the case. All right, so I again am checking a point in the second derivative. I'm going to use 0 here because that looks like a nice, easy number. If I plug 0 in for x there, that gives me 6. It's positive. And since this is positive, that means it is concave up. So that now is taking care of the intervals of concavity. Now we go on to the points of inflection. Now I know the -1/4. Now I needed to take that and figure out what the other coordinate is. Now this point of inflection, it is actually telling me a point on the graph. So like if I'm going and making the graph of this, like you're going to be doing tomorrow, if I'm going to go and make the graph of this, that means that this is an actual y-coordinate on the original graph. As in, I'm plugging it into f of x. I'm not plugging it into the derivative, not into the second derivative. It's going into the original function because I want just a y value, just a coordinate. So let's plug that in here. I want to know what is f of -1/4. When you do that calculation, when you plug it in for f of x, you should be getting a y-coordinate of 2 5/8, or 21/8, or 2.6125. Any of those would work. They're actually telling us where it's located, so again, remember this is a point I can plot, and we'll be able to use in actually making the graph as part of the bigger picture of all that other stuff we figured out how to find, like local max, local min, etc. Go ahead and do this problem now on your own. Do it first, and then we'll check it against the answers that we do here together. First thing you need to do is find the first derivative, and then use that to find the second derivative. And once you find the second derivative, we set it equal to 0, and then solve that for x. And you should get an x value of 1/2. In this case, again, we just have a single x value. Sometimes you will get more than one x value, and if so, you'll have to put them all in. All right, and then with that 1/2, I now know what my intervals of concavity should look like. It's just a matter of determining whether they're positive or negative. So I take a point from that first interval, such as 0, plug it into the second derivative. Remember, it's got to be the second derivative because we're trying to determine concavity. And when I plug 0 in there, that gives me a positive number, so that is concave up. For the second one, I plug in a number such as 1, and I find that one is concave down because it's negative. So that takes care of the intervals of concavity. And then we look for the points of inflection. I already know the 1/2. In order to find the y value, remember that we're plugging it back into the original function. So I'm figuring out what is f of 1/2 to find the y-coordinate. When you do that work, you should be getting an answer of 3/2, 1.5, 1.5, however you wanted to write it. And then I actually have the coordinates of the point of inflection, and I'm done with that part.